Hello. Take a look at this. So there's nothing on this graph apart from straight lines. And yet there's this curve that jumps out at you, isn't there? Let me put it in red. So it's called the envelope of this family of straight lines. And the purpose of this video is to explore the situations under which we might expect there to be an envelope and see how to conjure up the equation of the envelope from an equation that gives you all the straight lines. And I say conjure deliberately because there is something of the air of a conjuring trick about this little piece of mathematics. But unlike a magician, I'm going to show you how it works. Now, of course, I'm really thinking of an infinite family of lines here. So let's put the whole lot in. So we're thinking of a family of straight lines by parameterized by some variable t. So infinitely many of them, and they're all tangent to this envelope. That's the defining characteristic. They're all tangent to something. Okay, so that's the title. So before we get started, it's worth saying not only straight lines have envelopes. Here's a bunch of circles that have an envelope, which is in fact these straight lines. That's quite cute, isn't it? But for this video, it's just going to be straight lines. So it's simpler. And because I think it's rather pretty the way you get a curve jumping out from a bunch of straight lines. Um, Even if you have straight lines, you don't have to have an envelope, of course. Here's a family with no envelope. And here's another where the lines are higgledy-piggledy all over the place, and there's no chance of an envelope, is there? So I said the curves have got to be quite nice, but the family's got to be quite nice as well. So it's got to be a sort of continuously variable family. So let's take a first look at the algebra. Here's the way you would want to describe a family of curves. So t is the parameter. And so for each t, this here is a function of x and y. And setting that function equal to 0 would typically specify a curve, wouldn't it? A curve in the plane. So we've got a family of curves. There's another way to think about this, which is that here it's just the same. If t is for a particular value of t, this is the function of x and y, and setting it to 0 gives you a family of the curve. But now we can think about this as a function of three variables. And so in order for these curves to have be tangent to an envelope, be tangent to anything, these have got to be differentiable curves. But now, in order for the family to be fairly nice, we want f to be differentiable with respect to t as well as to x and y. So then you get this nice smoothly variable, smoothly varying family of curves, straight lines in our case. Right, now let's go back to the picture. I'll take the envelope away and we'll take that one away as well. So what can we say about this envelope? Well, the defining characteristic, as I say, is that all these lines are tangent to it. That means that if the let me put the envelope back in actually. So if the envelope is curving in one particular direction, then it means all these lines are going to be on the outside of that curve. And if we had them all there, this whole bit of the plane would be blue and this bit would be white. And so the envelope, in some sense, is the boundary between the blue bit and the white bit. Well, we'll see that cropping up again, but I don't think it's going to help us with the algebra, actually. But the way that does is to think about the intersection between one curve and its neighbour. So let's put those in, and I better zoom in so you can see better what's going on. So here we are. Now, all these intersections are very close to the envelope, aren't they? And you can see that if we had the more of the lines in here, the intersections would be even closer to the envelope. Let's look at this. So we get one of the lines here, and here is the envelope, and this is the point of tangency where the envelope meets the curve. So if we put a neighbouring line in, there's the point of intersection. We let this one curve approach the other one. Then the point of intersection approaches that point of tangency. In fact, it's sort of bound to, isn't it? So here we're getting the t value for this curve approach the t value for the one we start with, and the point of intersection approaches the point of tangency. Okay, let's look at the algebra for that. So where do these two curves meet? So this is the curve that gives us one family in the curve, one curve in the family, and this is the one that gives you a neighbouring curve in the family. So when they're both zero, that's the point of intersection. So if they're both zero, then so is their difference, um, and uh, and it's still zero if you divide by delta t. But if you take the limit of this thing, you get that. And look, this is f of t plus delta t minus f of t over delta t. So this tells you that at the point of tangency, this is zero and that is zero. So these two between them give you an equation for the envelope. Let's look at that. So we've got two equations with three unknowns. So for each t, this is two equations in two unknowns, x and y. And so that would typically specify a point, and that's a point on the envelope. Thinking of another way, if we eliminate t between these two equations, we get an equation with just x and y, and that's a Cartesian equation for the envelope. And putting it a third way, if you eliminate y from these two, then you get essentially x as a function of t. And similarly, you can get y as a function of t if you eliminate x. And that gives you then parametric equations for the envelope. So in a number of ways, you can see that having two equations like this specifies the envelope. So that's the formula for the envelope. Uh, Now, this business of differentiating with respect to a parameter is really rather bizarre, isn't it? So how are we going to understand that? Well, let me change that t to a z. So now it's the same equation, of course, but now this thing looks like, and indeed is, the equation of a surface in three-dimensional space. So let's look at that. So here's a surface in three-dimensional space. Well, you can see it's a surface. Let's just have a look around. You can sort of see it's a surface. Um, Now, to see that it's the right surface, we need to see what happens at a particular value of t. So let's put a plane in here. This is the plane z equals t for varying values of t. And that point A is just where it intersects the z-axis. So you can see what it's doing. So that's a plane there. And if you intersect that with the surface, you should get the curves, and there they are. So these are level curves on this surface, if you like. So they're the curves that correspond to our curves. Right, I'm going to get rid of the plane now, and let's rotate this thing again and look down on the situation. And here we have these curves, and you can see the envelope. That's quite cute, isn't it? So what can you see? Well, you can see, for one thing, that it is blue on this side and white on that side. But what's going on the surface at these? I'll put the envelope in actually. What's going on the surface at these points of the envelope? But the surface is sort of bending over and going under itself, isn't it? When you look down from the top, and what that tells you is there's a vertical tangent there. Put the tangent in. So here we are. So this um, envelope looks like this locus of points where the surface has a vertical tangent. Let's rotate it back to a more normal view. Now, so now the the envelope is in three-dimensional space. It's a bit complicated, but you can see, you can just about imagine that this envelope is the locus of points where there's a vertical tangent. Okay, back to the algebra. So what is this thing saying? Well, this one's saying it's on the surface, of course, but this, what does this say? Well, it says that if you vary z a little bit, and then the first order f doesn't change, so it's still zero. So as a first order, you're still on the surface. In other words, it's got a vertical tangent. So this is saying precisely that this is the locus of points where you're on the surface and there's a vertical tangent to the surface. So that's what the envelope formula is all about. It's instructive to do it in reverse. Suppose we start with a curve and generate all the family of tangents to it, and then we should be able to recover the equation of the curve by using this equation for the envelope. So here's a parametrically defined curve. So what's the equation of the tangent of that curve? Well, the tangent at the point corresponding to t is y minus this particular y over x minus this particular y is the gradient of that particular point. I'm using dot here for differentiating with respect to t, and this is the gradient, isn't it? So that's the equation of the tangent. So that is our equation f of x, f of f is equal to 0. That's a surface in three-dimensional space, if you like. So when we differentiate that, well, this we get use the chain rule, use the product rule. So this times the differential of that, that's that bit, plus this type and the differential of that. Well, but y is a constant in this context because we're doing partial differentiation with respect to t. So we just get this bit. On the other side, it's the same, and now these two a dot b dots cancel, so we get that. And so indeed, we do find that the original curve satisfies both these equations, and rather strongly in a sense, because it satisfies this, not only is that equal to that, but both sides are zero. And the same's true here, not only is this equal to that, but both sides are zero. So yeah, it definitely does. We do definitely recover the parametric curve. But it suggests, doesn't it, that there might be some other solutions to these two equations than the original curve. Well, I shall cover some of that in a future video. Just to finish off, though, let's apply this theory to this situation we started with. So what is this family of curves? Well, it's that. You recognize that probably. So this is a straight line that goes through the point naught t and 1 minus t naught. So I'll cross multiply that and differentiate, and we get that. So these two together are the equation for the envelope. So how do we solve that? Well, we eliminate t. So this one gives us that, and we substitute that into there. Well, I'll save you all the algebra, and what you get is that. So I don't know how good you are at recognizing conic sections from their equations. To some extent, I pulled the wool over your eyes here because this curve looks awfully like a bit of a circle, doesn't it? Well, it isn't. It's a parameter. It's a parabola. There, it's that parabola. Isn't that beautiful? So this is there's rather more of the family of straight lines and rather more of the envelope. In fact, what we've done in this video is show that if there is an envelope, then those two equations hold along it. What we shall do in the next video, look at situations under which those two equations hold, but they don't give rise to an envelope.